Hello, welcome to the course PH5 BO6 Electrodynamics 2. Today we are going to start module 3 transient currents, which is chapter 12 from electricity and magnetism by R. Murugesh. In the last two modules we have learned the fundamentals of electrodynamics, where we have seen the fields associated with moving charges and the interrelation between those fields. We have also learned, as a consequence of electromagnetic induction, whenever we try to change current in a circuit, there is a back EMF working against that change. Meaning, if you try to increase the current, the back EMF tries to decrease it, and vice versa. So what we are going to do in this module is, using whatever electrodynamics learned so far, we will try to analyze the behavior of current in certain simple electrical circuit. So let's start with an LR circuit where an inductance L and resistance R are connected in series to a cell of constant EMF E. So using a switch K, you can control the current flow through the circuit. When the switch is closed, the circuit is complete, current flows through the circuit, and when the switch is open, the circuit is broken and no more current flows through the circuit. Let's first discuss about the growth of current in the LR circuit. So let I be the instantaneous value of the current in the circuit. Now the first step in analyzing the behavior of any electrical circuit is to write down the EMF equation. So for that we need to first identify what are the various EMF or voltages involved. So you have a source voltage E, then the instantaneous current is I. When this current flows through resistance R, there is a potential drop IR across it. Also, the inductor is going to provide a back EMF given by minus L into di by dt. So you have three voltage components. So how to write down the EMF equation? So you have the source EMF E and L in di by dt. The back EMF is working against it. So the net EMF is E minus L into di by dt. So this net EMF or net voltage is going to drop across the resistor. You can write E minus L into di by dt equal to IR, or E equal to IR plus L into di by dt. So this is the EMF equation for LR circuit. So this is analogous to the equation of motion which we write in classical mechanics. So there you solve the equation of motion, you get position as a function of time. Same way here, you solve the EMF equation, you get current or charge as a function of time. So let's get into the business of solving this equation. So initially there is no current, and when the circuit is closed, current starts flowing. Slowly you have to work against the back EMF, overcome it, then you reach the maximum value I naught. So at the maximum value there is no more further change in the current, so di by dt is going to be 0 at the maximum value. So you can write, when current reaches maximum value I naught, this equation becomes E equal to R into I naught plus 0, or E equal to R I naught, and the maximum value of the current I naught is nothing but E divided by R. Now in this equation you can substitute for E. So EMF equation becomes R I naught equal to R I plus L into di by dt. Take Ri to the left hand side, you get R into I naught minus I equal to L into di by dt. Rearrange the terms, bring all the current terms together, you get di by I naught minus I equal to R by L into dt. So this is a simple first order differential equation. you can solve it by integrating once. So when you integrate, you get minus ln I naught minus I equal to R by L into T plus C, where C is the constant of integration. So we are talking about indefinite integrals here. So you have a constant associated with the solution. Now, how do you find out the value of the constant? You can use either a boundary condition or an initial condition. So if you are solving a time dependent equation like the one we are using now, then you need to use an initial condition where you will specify at time t equal to 0 what is the value of the function. Similarly, if you are using a space dependent function of x, y or z, then you can use a boundary condition. There you will specify at the boundary of the space what is the value of the function. So either using a boundary condition or initial condition, you can determine the value of the constant of integration. Here, since we are having a time dependent equation, we will use the initial condition. We know when time t equal to 0, and this is the starting position, there is no current in the circuit, so I equal to 0. So substitute this in this equation. So at t equal to 0, I equal to 0. So left hand side becomes minus ln I naught. On the right hand side, RT by L, this term gets cancelled. So I have only C on the right hand side. So value of C equal to minus ln I naught. Substitute for C in this equation, it becomes minus ln I naught minus I equal to R by L into T minus ln I naught. Rearrange the terms, bring the two logarithmic terms together, ln I naught minus I minus ln I naught equal to minus R by L into T, or ln I naught minus I divided by I naught equal to minus R by L into T. We can get rid of this logarithm here by taking exponential on both sides. So exponential and logarithm, these two cancel. So left hand side I have I naught minus I divided by I naught. And on the right hand side, exponential of this term, e to the power minus R by L into T. This you can write as 1 minus I by I naught equal to e to the power minus R by L into T, or I by I naught equal to 1 minus e to the power minus R by L into T, or the instantaneous value of current I equal to I naught into 1 minus e to the power minus R by L into T. So this is the current as a function of time. Now here, look at the exponential term. As you know, exponential is a unitless function, right? So which means the unit of t and unit of R by L, these two should cancel each other. So unit of t is second, so R by L should be second inverse. Or if you take the inverse L by R, it should be in seconds, meaning L by R refers to time constant of the LR circuit. Let's plot this solution so that you get an idea how is the current is varying. So how do we plot? Let's first find out what are the endpoints of this function. So starting point is the t equal to 0 point, and ending point is the other extreme, that is t equal to infinity. So at t equal to 0, you can substitute for t equal to 0 here. This is going to be e to the power 0, which is 1. 1 minus 1 is 0. So at t equal to 0, I equal to 0. So we have one starting point here at the origin. Similarly, at t equal to infinity, what happens? You have e to the power minus infinity here, which is 0. So I is going to be I naught. So other extreme point is I naught. And what is this function? This is an exponentially increasing function because you have a 1 minus e to the power negative term. So this is going to be, you have two negatives here. So end result is an exponentially increasing function. So you have an exponentially increasing curve from I equal to 0 to I equal to I naught. Now, what's the meaning of the time constant L by R? Suppose you put L by R equal to time t. Now substitute in this equation. So I equal to I naught into 1 minus e to the power minus 1 by t into t. This is going to be e to the power minus 1, which is equal to 0.632 I naught. So you can define the time constant L by R of an LR circuit as the time taken by the current to grow from 0 to 0.632 times the maximum value of the current in the circuit. Now, when you change L by R, time constant, how does the current vary? For that, let's take the rate of change of current in the LR circuit. So, rate of change of current is given by di by dt. From this expression, you can write down di by dt as R by L I naught e to the power minus R by L into t. Now, we want to find when you change L by R time constant, how does the rate vary? Okay. So, let's give two sample values to L by R. L by R equal to 1 and L by R equal to 2. For ease of analysis, let's assume that the maximum value of current in both cases is 1 ampere. So what's going to be the rate of change of current? Di by dt is equal to R by L, which is 1 into I naught, 1 into e to the power minus 1 into t. So let's look at the case where time equal to 1 second. After 1 second, what happens to the current? So exponential term is going to be e to the power minus 1. Okay, so do the math, you get 0.36. Similarly, when L by R equal to 2, you plug in the values, you get di by dt equal to 0.3. So when L by R value increases, the rate of change of current, the rate at which current is growing, is decreasing. In other words, greater the value of L by R, longer is the time taken by current to reach the maximum value I naught. So this is depicted in this graph here. You have three cases: large L by R, medium L by R, low L by R. So you can see here, when L by R value increases, it takes more time to grow from 0 to maximum value. In the case of small L by R, it increases rapidly to the maximum value. So this is the response of an LR circuit to the time constant. So that's about the growth of the current. Now suddenly when you remove the power supply from the source, you can do that either by removing and shortening these two terminals, or you can keep the battery here, just open the switch. In either ways, you are going to kill the current in the circuit. So how is the current is going to decrease? So current decreases from the maximum value I naught to 0. Once again, because of self-induction, there is a back EMF generated in the inductor. This back EMF is trying to oppose the decrease in the current. So as a consequence of that, the decay of the current is going to get slowed down. Once again, to analyze the decay of current, we need to write down the EMF equation. We have done that in the previous case, E equal to Ri plus L into di by dt. Now the power supply is removed from the source, so you can put the value of E equal to 0, substitute in the EMF equation, it becomes 0 equal to Ri plus L into di by dt. Rearrange the terms, bring all the current terms together, you get di by I equal to minus R by L into dt. This is a first order differential equation. Solve it by a single integration. You get ln I equal to minus R by L into t plus c. Once again, you can find out the value of c using the initial condition. So you started with maximum current. So at time t equal to 0, value of current is maximum. So you can put at t equal to 0, I equal to I naught. So put these values back into this equation. It becomes ln I naught equal to, this term gets cancelled because t equal to 0, and on the right hand side you have c. So value of the constant c equal to ln I naught. Substitute for c in this equation, you get ln I equal to minus r by L into t plus ln I naught. Bring together the logarithm terms, you get ln I minus ln I naught equal to minus r by L into t, or ln I by I naught equal to minus r by L into t. Take exponential on either side, exponential and logarithm get cancelled. So on left hand side you have I divided by I naught equal to exponential e to the power minus r by L into t, or the instantaneous value of current I equal to I naught e to the power minus r by L into t. So this is the value of current as a function of time. Let's plot this. So once again you have to find out the endpoints. So what is the starting point? T equal to 0. So in this function, if you put t equal to 0, e to the power 0 equal to 1, so you get I equal to I naught. What is the other endpoint? T equal to infinity, e to the power minus infinity equal to 0, so you get I equal to 0. So you start all the way from I equal to I naught and end at I equal to 0. And look at this function, this is an exponentially decreasing function. So this is the form of current while it is decaying in an LR circuit. An exponentially decaying function which decays from I equal to I naught to I equal to 0. Now, if you substitute L by R equal to T, current I equal to I naught into e to the power minus 1, or this is 1 over e into I naught. So substitute for e, you get 0.365 I naught. So you can also define the time constant L by R as the time taken by the current to decay to 1 by e times the maximum value of current in the circuit when the external source of EMF is removed. So you can define it either in terms of growing current or in terms of decaying current. Now, when you vary L by R, how does the decay change? So for that you need to find out the rate of decay of current, di by dt. So from the expression for current, you can calculate di by dt as minus r by L I naught e to the power minus r by L into t. This term I naught e to the power minus r by L into t is nothing but I. So this is minus r by L into I. So the rate of decay is directly proportional to r by L. Or you can say the rate of decay is inversely proportional to L by R. So when L by R increases, it takes more time to decay from maximum value to minimum value. So this is depicted in this graph. So you have three conditions: large L by R, medium L by R, small L by R. So when the time constant L by R is large, it takes more time to decay from I naught to 0. On the other hand, if the L by R value is small, it decays quickly to the minimum value. So if you look at growth and decay, these are complementary. Growth is exponentially increasing from 0 to I naught. In the case of decay, this is exponentially decreasing from I naught to 0. In this graph, you can easily make out what is the role of the self-induction here, or the back EMF here. So in the circuit, if there was no inductor, what happens? You have a power supply E which is connected to a resistance R. So moment you switch on the circuit, instantaneously the current reaches the maximum value I0. Similarly, when you break the circuit, instantaneously the current decreases to minimum value. But moment you introduce an inductor, because of the back EMF, there is no instant response, there is only a gradual response. So instead of instantly increasing from 0 to I0, this is gradually increasing from 0 to I0. Similarly, instead of instantly decreasing from I0 to 0, this is gradually decreasing from I0 to 0. And how fast the growth or decay happens, this is determined by the time constant L by R. So by manipulating the value of L or R, you can control the rate of growth and the rate of decay in an LR circuit. Let's do a quick problem. An inductor of 500 millihenry and resistor of 5 ohm are connected in series with a battery of 10 volt. Find the time constant and the final current. If the battery is removed and the two terminals are connected together, calculate the current after 0.2 seconds. So first thing, final current is the maximum current which is given by the source EMF divided by resistance R. So this is 10 by 5, which is 2 ampere. Time constant is L by R. So this is 500 millihenry divided by 5 ohm, which is 0.1 second. Now when you remove the battery, you want to calculate what is the current after 0.2 second. So when you remove the battery, current is decreasing, which is governed by the equation I equal to I naught e to the power minus R by L into T. You want to find out current after 0.2 seconds. So sorry, there is a typo here. You want to calculate after 2 seconds. Okay, so you substitute for T as 2 seconds. So this is I equal to I naught, which is 2 ampere into e to the power minus R by L. L by R is 0.1. So R by L equal to 10 into T equal to 2 seconds. So this is 0.271 ampere. So the initial current was 2 ampere. After 2 seconds, it decays to 0.271 ampere. So that's about growth and decay of current in an LR circuit. In the next class, we will learn about growth and decay of current or charges in a CR circuit. Thank you.